Now, as far as destruction and RBDs go, quite a few things need to happen. So if we look at the final result, here I have just the rendered base layer of our project, so without any of the lighting effects. This is the first layer that we are going to actually render, and then add all of the other lighting layers and effects on top. But this is the layer where we can see best the destruction effects. So if I play this, here is where all of the magic starts. So right as the character slams the magic ball into the ground, so to say, we have our initial impact, and this is a slow motion speed ramp kind of effect. So this is the first thing that we'll have to do. We'll see how we can create this speed ramp effect with RBDs, and the next part of this will be how to transition the animated version of our pieces into an actual simulation. So if I just go frame by frame in the render here, we can see that at some point right over here, the pieces return to sort of real time, and now they are actually simulated. So in between a couple of these frames, we go from animated pieces to simulated pieces. So this is the first thing that we will have to achieve. And then if we play the animation forward, we have a rather regular RBD simulation, but in the second part as well, where our scatter lining hits, we will also have to take certain things into account. And this will mostly concern using a custom attribute, which will be a vector that drives the pieces flying up depending on where the lining hits. So this will not be a regular RBD simulation where we would use collisions to drive this sort of effect. We are actually going to activate our pieces and use a custom vector to throw them in the air, so to say, and then layering all of these effects together in a single simulation. So the animation here, the transition into regular simulation, and then the second part of our scatter lining, all of this will be a single simulation at the end. So again, there's quite a few moving parts here, and I wanted to do a quick overview over each individual part with some simple examples before we actually tackle all of this in our main project. So if I step over in Houdini, I have a few examples here set up, and let's look at our first one. This will be mainly concerning the animation part of our simulation. So I have a simple box on which I use to create some pieces. So if I go at the Voronoi fracture, this is a very simple setup. This will not be the fracturing method that we are going to use. We are going to do some advanced fracturing, but just for explaining the RBD simulation, I just created a very simple fracture geometry. So if I do an exploded view from here, this is what we have. So from here, we assemble our pieces in order to simulate them later. And here we have a setup based on the transform pieces node, which we can use to animate the pieces, and we end up with something like this. So if I go at the end of our chain here and I press play, we end up with this animation. So in this node here, this is not running through a simulation. I'm simply animating the pieces by keyframes using the transform pieces. So here is actually where all of the magic happens in this attribute VOP, which is our template points that will drive the position of our pieces, as we can see. And we will recreate the setup in a second. So we have our animation, and then here we have to somehow transition from this animation into an actual simulation. So inside this .NET, if I take a look at the result, we have our initial animation, and then at a certain frame, we can see that the pieces go inside the simulation mode, and they also move in real time and maintain their original direction and sort of direction strength. So they kind of retain their momentum from the animation, and then also gravity can take place from here when they transition into the animation, and from here again it's just a standard DOP simulation. So we'll take a look into how we can create this. And for our second part, for the scatter lining, I have another simple setup here, and this is using collisions to drive these animations. So if I play this, we can see that for the most part, this provides a pretty good result. So this is also a method that you can definitely use to create this type of effect. but the actual method that we are going to use in the project is going to be the version that's being driven by an attribute. So in this version over here, which says attribute driven, we are going to create a direction attribute which will control our pieces flying upwards. And if I look at the points that belong to our pieces, I also have a visualizer for this attribute that we are going to create, and we can play the animation and see how our attribute will drive our pieces. So doing the RBD simulation this way, we are going to have a lot more control over the look, and it's going to provide us with the most amount of art directability, which is always a thing we should strive for in our setups. Because now, for example, I can go inside this attribute VOP where we set up this direction attribute, and for example, we have a noise that's randomizing the direction, and now all I have to do is change the offset if I want to change their direction, and I can increase the amount of randomness that we are adding and also the frequency and the roughness. And we can also have this visualizer here, which is sort of like a real-time representation on the path that our pieces will take. So this setup will allow us to have a lot faster iterations time, and we will know ahead of doing the actual simulation how our pieces will behave. And all we have to do now is go back to the .NET and I'll turn off the visualizer for now, and if I reset the simulation, now we will have a different path for our pieces. Also with this method, if I go inside, and we are going to set all of this up in a second, we have the ability to control how far the pieces are flying upwards. So there's a multiplier here, which if I set to a value of 2, we will now see that our pieces only travel half the height that they previously had. Okay, so we can also control this, which is really important. So let's go ahead, I'll go up and let's start with our first setup and see how we are going to create this impact animation with our pieces. So I'm gonna go ahead and I'll just grab this setup with the fracture. I'll press Ctrl C and let's just paste these over here. So this is just a simple box from which we generate a density volume, and then we apply some noise on this volume, and then we just scatter some points. So we get this nice uneven distribution, and we are using these as the cell points inside a Voronoi fracture. And again, if I drop down an exploded view, we end up with something like this. So just a very simple fracture, just for the sake of this example. Let's go ahead and from here, I'll just drop down a null and I'll rename this to initial fracture. And from here, because we are going to eventually feed all of these pieces inside a RBD simulation, we are going to have to work with packed geometry. So from here, we'll just do an assemble and we will turn on create packed primitives and just make sure that this create packed fragments options is also on, because this is what we need for RBD simulations. And from here, we can set up our transform pieces node. So if I do a transform pieces, we are going to need template points and rest points. So let's go ahead and turn our fracture pieces into points. We can simply do this with an add node. If I drop this down and select this option to delete geometry but keep points, we have now a point per individual piece. And the most important thing here, if I go to the information, is that we have this name attribute. So we are grabbing this from our assemble node. So it's really important that whatever points we end up with here have the same name node as our fractured geometry. So from here, I will just drop down a null and I can rename this to template points, and I'll drop down, or actually I'm just gonna go ahead and hold down Alt and duplicate this and rename this to rest PTS, and I'll plug this over here and our template points over here. And this is the setup that we need. So our rest points should be the same, and then inside our template points we can go ahead and create our movement. So for example, if I just drop down a transform node and I set the display to the transform, if I increase the uniform scale here, this essentially just spreads the points from each other. So if I look at the result from the transform pieces, we see that we are not really scaling up the pieces, we are just spreading them apart. So I can go to the transform here and we can see this more clearly. So this is what we need to do essentially, but of course we want more control and to introduce randomness and so forth. So instead of the transform, we are going to use an attribute VOP, and let's rename this to move pieces. we're going to keep this fairly simple, but in our project we are going to, what needs to happen here essentially is we have to create a vector and then add that vector to our points. And in this case, for this example, we are just going to create a vector that points to the center of the scene. So it's 0, 0, 0, but in our actual project, we are going to create it a bit differently to allow us the most art directability. So with that being said, let's go inside and we can just grab our position as it is. I will drop down a normalize. And if let's plug the position as it is in our output position. If I were to drop down and add from this normalized node, this will just create a vector that points to the center of our scene, because each position by default is a vector that's referencing the center of the scene. So if I just plug this normalize here, all of our points, we see that they are spread apart. So now we will need a multiplier to control this. Let's drop down a multiply. And from the input here, I will promote parameter and we will rename this to spread as the label. And if I go up, I can start and we can actually animate this value. So if I drop down a keyframe for value of 0 at the first frame, let's maybe move forward maybe 36 frames. And I'll just increase this value like so. And now if I go in the transform pieces, this is how we can create our initial explosions. So if I press play, we end up with this. Now, of course, we can go to our keyframes here. So let's shift click and we can create a exponential ramp to have this burst in the beginning and then a slowdown towards the second half. And this is how we can create this slow motion kind of effect. So if I press play now, we have this kind of animation, which is what we are looking for. And hopefully you can agree with me that creating this animation ourselves with a couple of keyframes is going to be a lot easier than trying to create an actual simulation and retiming that simulation. So that might have been the first instinct, at least it was for me. The first time I tried to do this effect actually was creating everything inside a single DOF simulation, but it was really hard to link, first of all, the impact part of the simulation with the scatter part as far as retiming is concerned. And it also didn't allow for the most amount of control on how our pieces are flying in this initial part here. And also this would be pretty hard to do if you were to animate the time scale in the simulation itself. So it goes from real time, which is a value of 1 to maybe 0.1. And then when our scatter happens, we would have to animate it again to a value of 1. So it goes in real time. And it was extremely hard to direct and pretty messy. So in the end, I found that transitioning from an animated state to a regular simulation allows the most control and is pretty much the most straightforward version that we can do. And we can see how easy this is with just a couple of keyframes to direct the speed. Now from here, we of course will have to introduce some randomness, and let's go ahead and inside this attribute VOP, let's randomize the multiplier of our vector first of all. And we can use a random from our ptnum. Let's generate a random value, and I will just directly plug this inside the multiply. So we have a value that goes from 0 to 1. Maybe actually let's use a fit range as well, and let's say that our destination mean should be at least maybe 0.3, so we don't end up with pieces that don't move at all. Okay, let's reset, and this is already starting to look pretty good, I would say. Let's also randomize the direction. So from our position, we can do a turbulent noise, and we will use a 3D noise and simplex. And let's add this after our normalize here for the position. We'll drop down and add, and we'll add this, and let's right click and choose to promote input parameters. And now if I go up, we can move forward a bit. And if I wanted to, I can increase the amplitude of this noise, maybe increase the frequency and the roughness. And again, this will allow us the maximum control, and we can, for example, if from our camera we are not going to like how our pieces are flying, so the trail they create, we can go ahead and we can just change the offset of our noise, and we will also be able to control the overall direction of our pieces as well. So we'll see all of this in the main project. But from here, we have enough information for our pieces, and we can move forward with the second part of this effect, which will be the transitioning to a regular simulation. So from here, let's set up our DOP.NET simulation. We'll drop down a null, and let's rename this to Geo, and we'll create a DOP network. Let's grab this Geo and let's step inside. So we are going to need a rigid body solver and an RBD packed object, and let's paste the SOP path in our RBD object to our Geo. Let's plug this in our second input and this into our output, and we'll also add a gravity force, and for now this is all we need. So if I press play, we can see that the cube simply falls down. So we will need to somehow tell our RBD packed object, or rather our simulation, that these pieces are animated and we want to preserve that animation. So for this we can use the animated attribute. So let's go up, and after our transform pieces we will do an attribute wrangle, and we will say I at animated equals 1. Now this is still not enough, because whenever we are dealing with animated fractured objects, we also have to make them inactive. So let's go ahead and also do a line here which says I at active equals 0, and I'll zoom in here a little bit. So we need both of these set in order for our animation to work in the .NET. So if I go back now and press play, we can see we have our animation. So we need now a trigger which tells our pieces to behave as normal RBD objects and for the rest of our simulation to take place. And for this trigger, we can simply look for a certain frame where we want the switch to happen. So let's say that maybe at around frame 35, we will do this switch. So we can do this with another attribute wrangle at the SOP level. Let's do another attribute wrangle. And for the first one, we'll rename this to set animated and active. And for the second one, we'll rename this to switch. Let's do switch animated. Okay, so we will do a condition here based on the frame, and we can say that if, and in between parentheses, at frame is bigger than, and we'll add a custom channel for this. So let's do ch, and in between parentheses and in between quotes we'll say switch frame. So if this condition is met, let's say that what we want to happen is to turn the pieces active. So we will simply say here I at active equals 1, and let's create our channels, and for our frame number let's give this 35. So when we are on frame 36, our geometry will turn active, and that means that they're allowed to simulate normally inside our .NET. And if I reset the simulation, let's press play and let's see what happens. Now we see that we do indeed pass the 35 frame mark, and on frame 36 still nothing happens, and this is because inside we are not actually checking for this switch attribute wrangle here to happen. So if I go back inside in our RBD packed objects, we have to turn on this option here to override attributes from SOP. And when this is enabled, it will look at the SOP level to any attribute changes, and it will actually pass them through our simulation. So now if I reset and press play, we see that at frame 36, our pieces start to fall down. So they're not inheriting any motion from our simulation, because we aren't actually creating any velocities on our points. We are pretty much forcefully moving them into place. We are just changing their position rather than affecting their velocity. And this is why we don't have any momentums and our pieces just completely fall down. But we took care of the first part, which is creating this switch between animated pieces and simulation. And now for our momentum part, we will have to actually create a direction attribute which we can apply in our simulation. So in our move pieces attribute VOP, let's create a vector from this current position of our points to our initial position, so the place where they were on frame 1. And maybe I can actually duplicate this just so we can view this. If I duplicate this attribute VOP and get rid of the animation, I can template our move pieces points and go forward in time. And let's maybe just do a color for these, and we'll make these red, or rather pink, and for this one I'll make these green. So if I merge these, this again, everything here is just for visualizing purposes. I'm gonna delete all of this in a second, but in our merge node we can see that our pieces start over here where the points are pink. So from their new position where they are altered, we are simply going to subtract this position from its original position, and this way we end up with a vector that we can use to further drive the pieces when they are animated. So let's go ahead and delete this, and in our attribute VOP, let's step inside, and over here after this add node is where we end up with this new position. So what I can do, I'm just gonna go ahead and duplicate this global node over here so we can use the position. Let's go ahead and let's do a subtract from our add, and let's actually place this below, and we want to subtract their initial position. And now this subtract node will create this vector that we want. So let's do a bind export, and we will name this attribute dir. And dir is just really an abbreviation I like to use that stands for direction, but obviously you can give this whatever name you want. But now if I were to preview this dir attribute, I already have a visualizer for this. Let's make sure that this is a 3 floats. And it seems that for some reason this isn't working, and I believe that if we duplicate the geometry VOP global, we are going to grab the position as it is right now, so after this add node. So what I have to do instead is actually make sure to plug our original position from here. So from our initial VOP global, let's go ahead and drag this over here and replace our VOP global too. So in this case, duplicating the geometry VOP global doesn't work. I'm gonna go ahead and get rid of this. And now we can see our direction attribute. So this is our dir. So now we can go ahead and bring this in our DOBNet simulation and see how we can use it. So let's go up, and inside our DOBNet, let's step inside and let's do a geometry VOP and plug this in our post solve. And inside we'll go ahead and let's do a bind import on our dir. So name here will be dir, and let's set this to a 3 floats, and we want to update the force vector with this. So if I plug this directly in our force, let's take a look and play the simulation now and see if something happens. So currently nothing is happening, and I believe that is because we have to scale up our dir vector quite a bit. So let's do a multiply, and let's promote our second input here and rename this to global, or let's actually do dir strength. And if I go up, let's set this to a high value like 100, and let's see if our pieces do something. And still this doesn't work, and this is because we have to specify in our RBD packed objects, we have to transfer over our dir as well. So over here in this list of attributes that we are grabbing from the SOP level, let's also add our dir attribute. And on this note, this dir attribute doesn't currently exist on our fractured pieces. So if I go up, if I look at the geo node, we can go to the information tab here and we can see that we don't have this dir attribute. And in our transform pieces, we have to actually specify that we want to copy this dir attribute. So we can see that as I turn on this toggle to attributes to copy, it will by default grab all of the attributes that we have on our template points. But in this case, I just want to transfer over this dir attribute. Okay, so I'll specify here attribute dir, and if I go to the geo information tab, we have this dir attribute here. And now in our DOBNet, let's go ahead and turn off the visualizer. We should have our pieces moving along our dir attribute. Okay, and here we have it. We can see that the strength is rather high, and we can also see that we are constantly updating this dir. So we can see that our pieces are exploding forever, and we can simply scale our dir attribute with another keyframe here in our attribute VOP. So we know that our transition happens at around frame 35. Let's go ahead and let's step back inside. We'll do a multiply here, and let's promote the second input of this multiply. And over here, this let's also give this a label name. We'll say that this is the strength. We'll want to start with a value of 1, and we'll add a keyframe, and we want to fade this off maybe over a duration of 5 or so keyframes, maybe at frame 40. Let's set this to 0, and now we should have more of that burst type of animation. So if I press play, here we have it. And we can go back inside, we can go to the geometry VOP here, and we can reduce this strength, let's say maybe a value of 50, and let's press play. Alright, and here we have it. Now we can see, and this is a common thing that happens with RBD simulations. If I look at this simulation frame by frame, we can see that a lot of these pieces that are smaller are flying way further out than the rest of the pieces that are larger. And to ensure that our pieces are receiving a more consistent amount of force, we can scale our force vector with their mass. So let's go inside, let's do a bind, and we'll bring in the mass, which is a float vector. And this mass is something that we get for free whenever we bring in the pieces inside an RBD simulation. So in the RBD packed objects, this mass is automatically calculated per each piece depending on how large their volume is. So all we have to do here is just plug the mass inside our multiply, and if I press play, now we should have a more consistent spread, or rather force applied to all of our pieces. So we end up with something like this, which is what we want. Of course, we can go ahead and randomize this dir attribute more and add all types of noises to maybe break up this spreading effect. But for now, this will be the first part of our effect that we have to take into account. So now we know how to transition between animated geometry and also how to animate the pieces, and then have them transition into a normal simulation. And this will be the first layer of our fracturing. And let's take a look at the other two examples and see which is the best way to handle the scatter part of this effect. For our scattered lining, let's take a look at the example where we have the RBD simulation being driven by a collision. So we have a simple box here that's going through an RBD material fracture. So if we look at this result, let's do an exploded view from here, and these are our pieces. And I'm placing this inside a group, which is selecting everything except these boundary edges over here. And I'm setting an active attribute only for these pieces down the middle. And then we are also using constraints in this case to keep our pieces together until our collision goes through the pieces. And I'm also increasing their strength here with an RBD constraint properties. And over to the right, we have a simple geometry that's being animated, running through all of the fractured geometry. So if I plug this, in this case I'm using the RBD bullet solver just because it's simpler, it's faster to set up, and this is just a demonstration on what this result will look like. So if I play the simulation now, we see that we get what we are looking for, and for the most part this is a pretty good result. If we had more detailed pieces, we can kind of get a pretty cool look, I would say. But for example, this setup doesn't allow us to specify really the direction of our pieces. So for example, if I want the pieces to sort of spread out more towards the side rather than up, we can't really control this that much. And we also can control the height at which the pieces are flying to. We can pretty much only modify this collision geometry in this case. So for example, maybe with the sweep node, if I want the result to be a little bit more chaotic and I want more destruction happening, I could simply increase this, so we can use the curves geometry of our lightning to create new collision geometry. So in this case, we can increase the radius of the collision geometry. And now if I play the simulation, if I just reset the simulation, we can kind of see that we get a result that's a little bit more chaotic. So we have more spread on our destruction and the pieces are kind of flying a little bit more. So there's more height to them. Now, in this case, we can also kind of see that our pieces are getting stuck slightly on our collision geometry. So when the pieces are flying up, they are also being pushed to the side by this collision geometry. And I'm not sure how noticeable this is, but this might not be a desired result. In this case, I believe this would work just fine. But again, we are looking for the maximum amount of art directability. So we are going to set this up by creating this direction vector ourselves. So let's go ahead and over to the right, we have our setup, which is using this vector attribute. And let's go ahead and build this setup. So I'm going to go ahead and I'll grab the box and the RBD material fracture just so we have the pieces. I'm going to go ahead and Control C and let's paste these over at the bottom. And also I'm going to go ahead and grab the line and the transform and just these two nodes for now. Let's paste them. All right, so we have our pieces. If we do an exploded view over here, and maybe I can do a null from here, and let's rename this to geofrac. And over to the right, what we have here is just a simple line which is animated across our box. So if I template this, we can see how the line travels through our geometry. And this simple curve will represent one of the lightning branches in our main project. So let's see how we can set up the simulation. From our geo over here, we will have to first of all assemble this geometry and create packed primitives. And there are a couple of things that need to happen in terms of attributes. First, we want to make our pieces active. Let's maybe just set an exploded view here with a low uniform scale just so we can see our pieces, and I'll template the curve geometry. So the first thing that we need to do is set all of our pieces as inactive to begin with, and then based on the proximity towards our curve geometry, we want to turn these pieces active as our curve geometry passes through. So from the assemble here, we can plug this inside a solver node. And I'll also bring in our curve geometry and plug this here. And I'll get rid of the exploded view for now. So we want all of the pieces to start as inactive. So I will add an attribute wrangle here after the assemble. We will run this over the points because after we turn them into packed primitives, these are essentially points. So from this assemble node and onwards, we are basically just dealing with points. So inside this attribute wrangle, let's do active equals 0. And we will want to set them as active based on our line geometry. So let's go ahead and let's rename this attribute wrangle to set active. And I'm going to go ahead and duplicate this over and attach it to our curve geometry. And for this one, we will say that at active, so I at active equals 1. And then we will do an attribute transfer inside the solver for this active attribute. So let's step inside, and for our previous frame, we'll do an attribute transfer. And we want to point this to our second input. So our first input is our own geometry, which is the fracture geometry, and our second input is actually, if we preview this, we can see that this is actually the curve. So in this attribute transfer, let's go ahead and only transfer this active attribute, and I can turn off primitives in this case, and let's just keep this at active. And let's go ahead, and in order to preview this, there's a trick that you can do here. I will go ahead and from the solver, I'll drop down a null, and let's say that this will be our RBDs. So I'll just rename this RBDs like so. And this is what we are going to provide inside the RBD packed object in the DOBNet simulation in a second. But in order to preview the attributes on our geometry, we can drop down an add node from here, and we can delete geometry but keep points. So now I can go to the information here, I'll click on active, and let's create a visualizer for this active attribute. And let's go ahead and set this to we'll keep this at ramped attribute active, and this should be fine. So if I press play now, we can see that after our first frame, when our solver starts, our points, let's maybe also turn these points, go to the geometry here and increase the point size so we can see this better. We can see that our points are starting to turn red as our line geometry travels the points, so maybe I will also template the line, and we can again see our points turning red as our line passes through the geometry. Now currently let's pin the viewport to the top level and step inside our solver, and inside the attribute transfer let's go ahead and I will decrease the distance threshold. Let's reset the simulation, and probably something like this looks to be all right. Maybe I can increase this further. So this distance threshold here will eventually determine the radius, or rather the spread of our flying pieces. So let's reset, and I believe a distance threshold of 3 maybe in this case should be all right. So now we are slowly activating the pieces, and let's go up and we can start setting up the simulation. We'll grab this RBDs null that we created, so let's Control C. We'll do another DOP network. Let's step inside, let's do RBD packed object. I'll place the saw path to our RBDs, and let's connect this to a rigid body solver and also a gravity node, or rather a gravity force. Let's plug this here, and already we should, let's also just straight away turn on this override attributes, because we want to keep reading continuously our active attribute from the sub level. And now I can unpin the viewport so we can see the actual result, and we can already see as I run the simulation that our pieces in the middle are slowly activating, so the gravity force can take place, and this is the result that we have so far. So now what we need to do is create this direction attribute, and again we will use the dir name in this case as well to create this attribute. So let's first let's go up, and after the solver let's preview the add version instead with just the points, and we will do an attribute VOP after the solver, and let's rename this to set dir, and we'll create a simple attribute that points up and just add some noise to it. So let's step inside, we will do a constant. Let's set this to 3 floats, 0, 1 and 0, and let's do a bind export and export this to our dir attribute and set the type here to 3 floats. So now if I go up, I should be able to visualize this dir attribute, and here we have it. And let's go back inside and also add some noise. So we'll use some turbulent noise from the position. Let's set this to a 3D noise simplex, and we'll do an add operation on our constant. And let's also promote our input parameters, and if I go up, I can now, maybe I'll start with increasing the roughness and the amplitude, and we can see the direction our pieces will have now. In the actual main project, we are going to spend a little bit more time to create an attribute, or rather the direction attribute, to have more controls. So we are going to make the chunks fly upwards but also to the side, and we are going to add some controls to determine how much of the up direction and how much to the side direction the pieces should have. So just a quick note that we are going to create a more advanced direction attribute. But now that we have this dir attribute, in order to use this in our .NET, we can do a similar thing to what we did in the first example. So let's step inside the .NET and we'll do a geometry VOP. Let's connect this to our post solve, and let's go inside and do a bind import on our dir attribute, and let's set this to a 3 floats. So don't forget to specify the type whenever you are doing or whenever you are importing an attribute. And again, here we want to update our force. So if I just plug this into the force, and let's see what happens. And before this, let's go up and let's go to our RBD packed objects, and again we will want to make sure that we are bringing in this dir attribute on this override attributes list over here. So make sure to add this over here. Let's get rid of the visualizer and let's press play and see if we are getting something. Currently the gravity force, I believe, is still too strong. So let's go back inside here and add a multiplier for our dir, promote the second input, and let's rename this to strength. Let's go up and let's set this to a value of 50 and let's press play. So still nothing is happening. Let's also multiply this with our mass as we did earlier. Let's do another bind and let's bring in the mass as well and plug this inside the multiply and let's press play. Okay, so now we are finally starting to get something, and what's happening currently is the pieces are just completely flying upwards using this dirt direction that we set up, but they are no longer falling as well. So this dir vector that we're creating is continuously pumping in this direction in our force output, and the gravity can no longer take place. The gravity is still affecting our pieces, but the dir attribute is so strong that it's not really showing. So this gravity force. So in a similar way to how we keyframed the scale of our dir attribute at the sub level in the first example, if we remember over here where we created our DOBNet, in our attribute VOP where we created the dir attribute, we have a multiplier that we keyframed from 1 to a value of 0 over a duration of 40 frames. And now what we have to do, we can have to do the same thing in our new setup, but we have to do this procedurally based on where our curve travels. So we want this dir attribute to have a strength of 100% where our curve currently is inside the geometry, and then as it passes through the geometry, these pieces that are left behind, we want their force, we want the dir force for these pieces to fade to 0 so that gravity can take place. And what we can do is create an age attribute for our pieces based on where our curve is. And all we have to do, maybe we can preview this with our add node, and again we will dive inside the solver, so we will pin this viewport. Let's step inside, and after this attribute transfer, we can say, let's do an attribute wrangle, and we can say that if you are active, let's go ahead and increase your age. So we will say that if, and in between parentheses we'll say I at active is bigger than 0, we will say that at age plus equals 1. So this is a very similar technique to what we do usually when we are dealing with attribute growth or attribute propagation, where we are continuously increasing the age of the points based on a condition. So now if I go up, if I go inside the attribute VOP, and again we will just preview this through our add. Let's step inside, and if we want, we can grab the age from here, and let's run a fit range, and let's plug this in our CD because we can preview this through the color. We can set the source max here maybe to a value of 15. And we will also have to go up and let's reset the solver simulation so this updates properly. So reset simulation. Now we can see that over the course of 15 frames, based on the proximity to our curve, our particles start to age. So in this case, because we are fitting this range over 15 frames, these particles are going from 0 to 1. And what we can do is we can further control this with a ramp. So after our fit range, we will do a ramp parameter. And let's set this to a spline ramp. Let's go up and we will simply add one dot over here towards the beginning of our ramp, and as a result we have this value that we can use as a multiplier on our dir attribute. And if we want to control the spread, we can go inside here, and all we have to do is change the source max in our fit range. So if I promote this parameter and go up, I can increase this maybe to a value of 25, and now we can see that we can really control this fading of our attribute, and I can maybe add another dot here to control this gradient more, but for the most part something simple will be fine. So all we have to do now is just simply multiply this with our dir. So I'm gonna go ahead and grab all of these nodes, and instead of updating the color, we'll just use this as a multiplier. So let's maybe do a multiply before we export our dir attribute, and let's plug the ramp inside the multiply. Let's go up and we can preview this dir attribute now with a visualizer, and this is what we end up with. And maybe actually inside this visualizer I'll go over here and let's just increase the line length so we see this more clearly. Okay, so now we can see that as our curve moves through our pieces, they will receive the full strength of our direction attribute, and then fade off over time. So if I go to the simulation now, let's go ahead, let's play and see what we get. All right, still we should probably scale this down by quite a lot. Let's use a value of 10 instead over here, and we'll also combine some other nodes as well in the main project, but for now we'll just simply do a pop drag and we'll decrease this to maybe a value of 0.1. So let's go ahead and press play, and this is now too low. Let's go ahead and set this back. Let's try 35. All right, so now we are starting to get the result that we are after. And by controlling this strength, we control really how high our pieces can get. So if I want the pieces to not fly up as much, we'll just decrease the strength over here to maybe 25. All right, so now this decreases the height, which is great, and this is what we wanted, this level of control. And now we can also go up, and if I wanted more randomness, I can just go to the dir attribute VOP over here and I can increase the amplitude. So we can, let's try an amplitude of 5 for our noise, and we can see how this will look in our points as well. And this is again also one of the advantages of setting it up this way, because we have this visual representation on the trail of our pieces. So maybe I can increase this even more and I can play around with the frequency. So now if I play the simulation, let's see what we get. Okay, so a lot more chaos. And again, in the main project, we are going to create a more intricate setup for our direction vector. But this is the base of how this setup will work. And what we'll have to do in the main project is first create the scatter simulation. So this part over here, let's maybe look at our render result. We'll have to set up this simulation first for our scatter lightning, and then we'll have to layer in our first impact animation. So we'll actually do this part second after we create the scattered part. So we'll see exactly how this will work in the main project, but I just wanted to give you a overview on all of the techniques that we are going to have to use and blend together to achieve the final result. So I will highly encourage you to try some of these setups first in this sort of easy mode version before following along with the project where all of this is blended together, because when we do this setup it will get quite complex. So we have to make sure we understand all of these individual steps first. Alright, so with that being said, I'll see you in the next lesson.